Okay, so 7.3 sampling distributions of means. And of course, the keyword here is means. So what we're still talking about is that same idea of if I got a population and I'm going to take a sample out of it, then I'm going to create a statistic, right? The statistic that we're worried about right now is means. So if I had a mean of 3, but then I'm going to go in, I'm going to take another sample, same size, I'm going to get mean of that, and that mean maybe it's 2. And then I'm going to go take another one, and I'm going to get another mean out of that, and that mean is 3 again, and so on and so forth. And so now I'm going to just create a sampling distribution based around some different values, right? 1, 2, 3, 4, 5, or whatever. And then plot, well, I got a 3, I got another 3, I got a 2, and then maybe I got some in between. And then I just start stacking them all up, right? And this is a bunch of different sampling distributions. This is all my dot plots. Just keep stacking, 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 and so on and so forth until we create an entire sampling distribution, right? But that would need to be, again, reiterating, all possible samples of the same size, right? They create a sampling distribution. Now, again, we know, as we've been talking about, that cannot happen. That's just going to take way too long. But we do know if we're talking about means and we're taking and trying to build a sampling distribution, certain criteria will be met. So again, just like with proportions, we just need to figure out what is the shape of this distribution going to be, what is the center going to be centered around, and how wide is this thing going to be. And this is all going to be based on knowing what happens as we start to create a sampling distribution over and over again. So certain criteria is made. So let's talk about these. All right, let's do it. Let's do shape. The shape is going to be, you ready for this? Approximately normal. But it is only going to be approximately normal when certain things happen, right? So it's kind of a twofold thing. It's going to be approximately normal, the sampling distribution, if the population is approximately normal. Okay, so essentially, a sampling distribution of means takes on the shape of the population distribution. So if the population, I guess I could write that distribution, is approximately normal, that's good. What if it's not? There's a secondary check that we can say if the sample size is greater than or equal to 30. Well, that is strange. Let's take a little side tangent here. Why is this true right here if n is greater than or equal to 30? Well, what researchers have found is that they just messed with different sample size. Let's take sample size of 10. Let's take sample size of 20. Let's say sample size of 30, 40, 50, 60. And they took the means and they started building these sampling distributions. And what they found was there was a threshold here. If the sampling is in fact 30 or greater, that it will start to take on an approximately normal shape. And that's crazy, right? So they tried it over and over again. They tried it again. They tried it again. And in fact, 30 is the threshold. When you hit 30, sample size of 30 or greater, your sampling distribution will. And so they've named this thing. This thing is called the central limit theorem. I do want you to know that. Yes, central limit theorem, because I can hear you saying, I wonder if I should write this down. Yeah, write it down. CLT is sometimes how it's called. Here's what the central limit says. If we have sample size of 30 or more, then the sampling distribution of means, right? So that means I got to be looking at the means, not the proportion. So sampling distribution of means will take on an approximately normal distribution. Approximately normal distribution shape. That's what I meant to say. Yes. So this is a guarantee. Central limit theorem guarantees that if we have sample sizes of 30 or more, then the sampling distribution of means will take on an approximately normal shape. That is called the central limit theorem. So that's been dubbed. It's a theorem. It's something that it was a theory at first. They tested it. They have not been able to disprove it. Therefore, it's become a theorem. But here's the idea. If we're talking about means, and this is the important part, we have to be talking about the sampling distribution of means, not of proportions. But if we're talking about sampling distribution of means, number one check. If the population distribution is approximately normal, we are good no matter what sample size we have. But if we don't know what the population shape is, and we're taking sample sizes less than 30, there's no guarantee that it's going to start becoming normal. But once we hit the threshold of 30, then our shape does start to become normal. Wow, so okay, that's good to know. That's our shape, approximately normal. All right, let's move on to the next piece that we need to know then. I'm going to need to know, where is my center? Well, being that mean is also an unbiased estimator, very much like proportions is, the average of the entire averages. So if I put all those averages on their own little distribution and I averaged all the averages, the average of the averages equals the average of the population. Whoa, that's a lot of average, right? But essentially, here's what it says, is that when we create this sampling distribution, that if I were to average out all of those things, it should average the true population parameter because it is unbiased. Now, how do we try to make sure things stay unbiased? We take a random sample, right? Remember, that's how we try to reduce bias. So unbiased means for the average of all the averages to equal the average of the true population. Okay, well, that's good to know. And what about the spread? Well, let's talk about standard deviation. So the standard deviation of the averages is going to be equal to the standard deviation of the population divided by the square root of n, right? But we know standard deviations only work if, let's write this out, number one, if we have independence. What if we don't have independence? Remember, as we learned from proportions, that if we don't have independence, we could still violate independence as long as we consider the 10% rule. If you remember, the 10% rule says that the population is bigger than 10 times the sample. Or some people like to say, or if I took 10% of the population, it is still greater than or equal to that sample size, whichever calculation you like to use. Right? So there it is. This is what we need to know. We need to be able to always describe the shape, the center, and the spread. But there's certain criteria that come along to being able to describe it. If I'm going to say approximately normal, one of these two things has to be true. Population needs to be approximately normal, or the central limit theorem kicks in. To center, in order to be unbiased, we just need to make sure that we took it from a random source. For the spread to be a legitimate calculation, we need to be sure that it's independent, or if we are violating independence, don't violate it too badly, use the 10% rule. So that's what it would look like right there. All right, well, let's give this a shot. Let's take this. Let's say I went to Lake Ridge High School. Lake Ridge High School, population 1,200. I went to Lake Ridge High School, and I decided to take a sample of size 50, right? Take a sample of size 50, And I was trying to find out the average number of pets that students own. So out of my sample of size 50, I ended up with an X bar of 1.7. 1.7 pets that students have at their home, right? But then we say, you know what? We know that in the population, the true proportion is equal to 2.3 with a standard deviation of 1.2. Okay, so maybe that's known to us already, and we decided we're going to test that theory. If do I believe this is true? So I am going to go and do my own sample of 50. So before I even consider what my sample and who cares about my sample, what I really want to do is figure out based on my sampling distribution of size 50. So let's build the sampling distribution of means for samples size 50. All right, what are a few things that I need to know? I need to know, what is the shape? Well, what do we believe the shape will be? I think it's going to be approximately normal. How do I know? Let's check it. Let's do a check. And this is going to be important that we can always check. I don't know, Lake Ridge High School distribution of pets. Is the true population distribution of pets approximately normal? I don't know. It wasn't told to me. Well, what if it's not approximately normal? Well, then I'm going to do my secondary check. Is n greater than or equal to 30? You should say, yep. Therefore, central limit theorem. Then this is how you're going to show the check to an AP grader. Check central limit theorem. That guarantees an approximately normal shape. Okay, well, where is this thing going to be centered at, this entire sampling distribution? Well, the mean of all the means should be centered around the value 2.3. Let me check. Did I take a random sample? I don't know. Let me check for a random sample. So I probably should have said, I'm going to take a simple random sample of 50. Oh, okay, you said simple random sample? Check. That's good. Okay, so that now means it's an unbiased estimator. And what is the spread going to be on this thing? Well, by formula, it says the spread is going to be the standard deviation of the population divided by the square root of 50, the square root of n on here. That's going to require my calculator. 1.2 divided by the square root of 50. So it is going to be 0.17. Let's just go ahead and round that to there. Let me check that that actual calculation is going to be a good enough calculation. So I don't know if I'm taking students and asking them the questions and pulling them out, then I'm actually violating independence right now. But so let's do this. Let's do 1200. That's the sample size. See if it's greater than or equal to 10 times my sample size. So 1200 is greater than or equal to 500. Is that true? Yes. So the 10% rule checks out, and this is a good estimator. Okay, so now having all that knowledge, let's actually build this thing. So let's do this. 2.3, that's that right there. Okay, and then we know that these would be a certain length. Now, here's what I want you to understand is if I increase my sample size, look at this, if I increase the sample size here, guess what happens to my standard deviation? It continues to get smaller and smaller. So bigger samples create more condensed graph, right? And that's good to know. So if I get bigger sample sizes, it actually, we don't like to call the word accurate, but it starts to point better to the actual true values, which should make sense theoretically. If I took larger samples, like if I took half, like if I took a 500 or 600 sample size, that's going to give me a lot better indication of what's happening in that population than a sample size of 50, than would a sample size of 5. So think about that. That's, anyway, that's kind of a side note there. But let's say we did this right here. Okay, so then let's cycle all the way back to the original question. Was I got a sample of 1.7 pets? Do I believe in this number, 2.3? based on my sample of 50, right? So, well, that would be something we need to check, right? Does that seem appropriate to get that number? So what I'm going to do real quick, let's do this. Let's do z equals my number, which is 1.7. That was the mean I got, minus the claimed mean, which is 2.3, divided by this new standard deviation calculation that I just calculated for this entire distribution. So 1.7 minus 2.3 divided by 0.17 gives me a negative 3.53. Okay, so think about where that is on the graph. So here's one standard deviation, here's two standard deviations, here's three standard deviations, and negative 3, it's about right here. So there's where my sample lies. So probability, let's calculate probability. How often, so that's what I'm going to calculate now, this probability. I'm going to say this. How often should, remember, because this is theoretical, remember there's 1,000 million different samples all up underneath this thing, right? That's what this curve is representing. And I'm saying, how often should I get a sample mean to be 1.7 or less if the true population mean is 2.3? How often should I get that if that's true? That's called a normal CDF function. So I'm going to do a probability in my calculator to find that answer. So I'm going to go normal CDF. I'm going to go negative infinity to 1.7, and then my mean is 2.3, and my standard deviation is the one I calculated, 0.17. Let me paste all that in. And so I get, oh, it's e to the negative fourth. That is 0.1. 3 zeros, and then 208. So let's say probability is roughly 0%. I probably shouldn't have gotten that sample if the true population is 2.3. So going back up to the original question, do you think that this is truly the average number of pets that Lake Ridge High School students own if I ended up with this sample here, right? And it's all based on this theory here that if this is the true population 2.3, that this graph would happen because all the criteria checked out. And if this is the distribution of all possible samples, how often do I get one like mine? Well, the question and the answer is I should not have really ever gotten a sample like that if 2.3 was the actual population. So I do not believe that that is a good, true average for the Lake Ridge High School number of pets. So that's the analysis. That's actually what we get into second semester. What we're trying to do right now, this chapter, is build and find probabilities. Build and find probabilities, this stuff right here. Can I talk about the shape? Can I talk about the center? Can I talk about the spread? Can I build that graph? And then you can ask me any question you want, and I will find the probability. That's what we're doing for this one. This is the sampling distribution of means. Notice how nicely it parallels the sampling distribution of proportions.